Can you see my screen?
Yes, ma'am. Yeah.
Okay. So, I will talk about my work in algebra and whatever little more, hopefully slightly more wiser that I have become over the years with respect to algebra. So I'll also want to refocus some of my work to try and understand or answer the question, why teach algebra at all actually? Because it's not very obvious why one should uh, teach this thing if the only purpose of doing algebra is to gain some fluency with the language of mathematics, the symbols that it grants. Okay. So I'll go back and forth between what we see in reality and what we think about those. How do we reflect on those, some of those ideas? Uh, it's probably I'll have to move my thumbnails. I'll just get off. Okay. Um, I do not know, Varsha, how you do this all the time. Do you do a very interactive lecture? Do you take the questions only at the end? However you want it, I'm happy.
Ma'am, the speaker has generally 40 to 45 minutes and
Okay.
then we take Q&A.
Okay. Sure. Okay. So this is some data that I collected some years back from grade 7 students and their ability to work with slightly more complex set of symbols, which are algebraic in nature. So if you look at an example like this, so it's a very typical exercise for children in schools. You have to simplify this expression into the most common form that you can get. So the child starts fairly okay, does some moving around of the terms, gets the like terms together, does this step. But following from the third step, there are some very unusual things, not unnatural. These are very, very common. So 8x plus 2y becomes 10x minus 13. And then finally you get a 13x. Then there is another problem, which is on equations, although I'm not going to focus today on equations. So 5m plus, the first step once again is correct. And the child does the plus 9 minus 9 on both sides to sort of take away the 9 on the left hand side. But the second step is a strange step, dividing on the left hand side by m and on the right hand side by 9 for some reason. And then the child does something, gets a 9, and then says it's equal to 45. There's a 5 on the left, there's a 9 on the right. There are equal to signs all over. Please notice all of the placement of the things. Then there is a third problem. The child had to solve this arithmetic expression, and the child does 20. So the first step is sort of a repetition of the question itself. Then the child does something interesting, takes away all the 21s with whatever signs they had, takes away all the numbers which were multipliers on another side, works around with the additive terms and works around with the multiplicative terms, and does something and gets a large number. Now, these are classic cases of not probably understanding what these symbols stand for and what do we actually have to do with these symbols. Even if we say simplify, evaluate, solve, but what does it really mean to be doing any of these three things? So what we really see in these three examples are a classic case of what is called the conjoining, that in primary grades, children have this habit of writing an answer on the right hand side. So any problem that you give ends with an equal to answer. And that answer is always a single number. And that's what we see here also. The answer, the child brings it down to a 10x minus 13 and then a 13x. The equality, the equation solving question shows clearly a sense there is a lack of understanding of the equal to sign and equivalence. That is all. Equivalence runs through all the three problems. The third, arithmetic expression shows a lack of understanding of order of operations and properties of operations. We use several kinds of things like BODMAS and all, but the child clearly seems to have missed it. The problem probably is that children learn these only as rules, which are only half remembered. So the teacher might have said something about doing the same thing on both sides. The child remembers it for the first step by subtracting 9 on both sides in the equation. Tries to do something similar. The teacher would have said, you have to take away the m. The child divides by m and takes away the m, but doesn't know what to do on the other side. The teacher might have also several times told you have to collect like terms, but child seems to have missed the idea of like terms and instead reconfigured it as additive terms and multiplicative terms. So this could itself be a definition of like terms, which we may not necessarily always think of. Okay, so now when adults intervene, many of the times adults do things of this kind, which they find or call, this will be, ma'am, simple and fun. And by adults, these are several times my master's students or my BSc B.Ed students or even teachers in schools. This sort of set of examples belong to anywhere. So the first problem that so this is a plan that a student is making for going to school, and they decide to do this. In Nandi school, children are asked to donate items like books, clothes, and toys in an orphanage. So Ramu and his friends are donating the items. And then there is a table of Nandi Chantal expressions for each person, and add all the items and find the final list. Where is the variable? What is the need for a variable here? That's the question then. Yeah. So we feel that it might be very simple to do these kinds of things. Then there are other set of students who find that why should we even put X and Y? Let's just put nice, beautiful animals. So cat, butterfly, hen. But does it really make sense? If we were to make sense, what is dog minus 2 equal to 8? It can at best be number of dogs minus 2 can be equal to 8. But just by putting a dog, it communicates actually nothing, such statements. Then this is a grade 6 teacher trying to teach in class, and the grade 6 children of her class. So the teacher has done something on the board to the effect where she had written a relationship x plus 5. And the children immediately asked, ma'am, why did you leave it at x plus 5? Shouldn't it be 5x? So write equal to 5x. And the teacher tries to explain what she has done and why she has left it like this. So 5 pencils and 6 pencils is 11 so the children say 11 pencils. And then the teacher asks, some erasers and some pencils and some rubbers. And children say 11 again. And then teacher says 11 what? This will become stationary. It will no longer be pencils or rubbers. So 5p plus 5p is 10p. Now, do you see the relationship between this table and the simple and fun? This table on the left immediately about children donating books, clothes, and toys. 6p plus 7p is 13p. But what is 8 pencils and 5 rubbers? Can you tell the final answer? And children say yes, 13pr. And the teacher goes on to say that 8p plus 5r, this will be as it is. Now she sort of relinquished her desire to explain. 10 boys plus 10 girls, 20 students. So do you see what children are constantly doing? They're actually creating a super class from the subclasses that the teacher is categorizing her objects into. When things are different, you cannot add. What is x? X is a variable. Variable changes from question to question. Let x be girls, y be boys, and she draws a table of 6a and 6b. Changing x and y are variables. You cannot add them unless you're given the values of x and y. Therefore, x into 5 is 5x, but x plus 5 is 5. x plus 5. You're not getting a number. This is still a variable. So she tries in vain actually to communicate to children why x plus 5 should be left as x plus 5. Okay, now let's look at one more lesson very quickly. Um, so this is a grade 8 class, fairly complex class. The teacher wants them to apply a plus b whole square identity onto root 3 plus 2 whole square and expand it. And she does the basic minimal work of identifying what is the a and the b, and then what form will a plus b whole square will take, that is a squared plus b squared plus 2ab. And at this point, she also tells children that root 3x whole square is in the form ab whole square, which is a square into b square. And she cautions them, the square is applicable for root 3 and x, and therefore it should become root 3 square x square. Now, square root and square get cancelled because there was a root 3 and there is a square, and that's what she is indicating, 3 to the power of half to the power of square. Then one child just asks, shouldn't we just cancel the root 3 in 4 root 3x also? Because if it is a matter of cancelling, let's just cancel wherever it is. So then the teacher says, no, here no need. Why are we cancelling root 3? Because in the other case, when she did indicate that root 3 must be cancelled, she sort of indicates now that root 3 to the power of is equal to 3 to the power of half, and whole square of that is 2, and 2 will cancel. So what I wanted to bring to our attention is, in all these cases, we are just trying to invoke something to tell them that the rules that exist are inalienable and you can't change them. There is just something little I can do to help you understand, but that's how things are. Now, my little analysis of these will tell us a little bit more that when we move from arithmetic to algebra, there is a new set of symbols and a new set of conventions. And very simple examples like this, that David is 10 centimeter taller than Con. Con's height is 8 centimeter. What is David's height? And children give all these different responses. 10h, D, David's height is D. 10h means that there is some 10, there is some h, maybe it is 10 plus h is 10h. Then there are children who write as David's height as DH. So after all, since we use letters so much as short form for objects, P for pencils, R for rubbers, then why can't I just do David's height is DH, H equal to H plus 10. There are also children who write it as R, and I will leave you guessing what this R is. They write it as 18. These two are actually the interesting trick parts, 110, and they just choose that I'm not going to work with H, I'm going to replace it by 100, and then the height will be 110. So this typically, much of these interpretations is found in the fact that letter is treated as an object, and this is typically called the fruit salad algebra in the literature. So when 60 is equal to 12, it basically means for teachers and children, 6 donuts cost rupees 12. Okay. This is one set of issues that we find, that children and teachers in the everyday sense don't seem to understand that letters do not stand for short forms of objects. Then the other problem that we face with algebra is that for all the years in primary schooling, we would have written 2 1 by 3 as 2 plus 1 by 3. So when there was no sign written, it was actually an addition. 245 is 200 plus 40 plus 5. 27 plus 18 is 45 because we add them up. But then if all this were true, then h plus 10 must be equal to 10h. It's obvious, right? If this is not the convention of algebra, then it is on us to make it available to children in some way. And if all of this is true, then 2a plus 5b must also be equal to 7ab, while in contrast, in these conventions of algebra, it is a into b which is ab, not a plus b. Similarly, a question like 2a plus 2b plus 4, given a plus b is 25, only roughly around 1/3 of grade 8 students can do this. Yeah. And the reason is they cannot see 2a plus 2b. They can see 2a plus 2b as only a process where if I'm given a and b, I can plug in the values, I can calculate. But if I'm given a plus b, then I do not know what to do. Because the way to solve it is you have to do a structural manipulation of this sentence to make it twice a plus b plus 4. Yeah, which is what children don't necessarily imagine immediately. There are also another set of problems, and all this is driven for loads of literature. This is just a small minuscule of that. So children often would write 8 plus 4 equal to 12 plus 5. And they feel that 12 should be the right thing. In fact, there are some children whom I have noticed who will write 12 plus 5 equal to 17. They stop themselves only at when they get a 17. They also don't think you can write 8 equal to 5 plus 3. You should always write 5 plus 3 equal to 8. If you ask them to do a problem twice 6 plus 2, they are likely to write 2 times 6 equal to 12 plus 2 equal to 14. Everywhere there is no sense of equality or equivalence. And children often say that the 685 minus 492 plus 947 is the same as 947 plus 492 minus 685. Sorry, there's a typo. Uh, and these are the same because the numbers are the same. And the same is true for this. As long as numbers are same, they are not looking at what constitutes the expression and what constitutes its value. So this is what we call lack of structure sense. They do not know how these operation signs and the numbers together constitute the expressions and its value. So children also don't quite understand whether 23 minus 3 plus 9 should be done as 20 plus 9 or 23 minus 12. And why at all do these two things create different answers? So these are some issues that we know, that children have difficulty understanding the symbols and conventions and equality and equivalence. Now, in the previous era, I mean, whatever we have done till now is primarily to help children unpack these things and try to get their symbol sense better. But what I am arguing and what most people argue today, or maybe it's been since 2000s onwards, that we need to probably rethink and redefine what algebra is and our actions in that domain. So I'm going to slightly redefine algebra. It is the branch of mathematics that deals with the language for expressing generality and relationships, manipulating and reasoning about generality, including proving. It's a branch in which you create formulae for problem solving. You solve equations. And at a slightly higher level, you work with functions, formulae, tables, and graphs. And I'm not going to I'm not going to talk either about equations today or about functions. But why should we teach algebra? Algebra is actually a preparation for further education. It's also a gatekeeper for higher math. And if you don't have higher math, then your preparation for further education gets hindered. And therefore, algebra seems to play a very crucial role. But not only this very instrumental role, algebra does something which only the computational arithmetic fails to do, which is to add depth, coherence, and power. And I will show you simple examples of what depth, coherence, and power might mean in elementary grades. And this is, since it is such a powerful set of ideas, we need to democratize the access of this. And therefore, we need to teach algebra to everybody. So Caput, who unfortunately passed away very early on when he was at his peak of his work, actually, was very, very vociferous about democratizing access to these powerful ideas and not keeping them to the privileged. And especially in the US context, when streams get divided by arithmetic and commercial arithmetic, and algebra is a privileged stream that you can choose from grade 7 onwards. So we need to change algebra instruction. So, and for that, we need to make some assumptions that algebra is a cultural artifact, it's a human activity. and a self-sustained body of knowledge. One has to make the most alienating and difficult component of the curriculum in school mathematics more meaningful. We need to engage learners with purposeful tasks with meaningful outcomes, encouraging algebraic thinking, which include generalization, abstraction, conjecturing, etc. Give learners a feeling of empowerment that help them understand situations. Stimulate a feeling of intellectual fulfillment and aesthetics. Gain insights into something. I wish I had, we can, I'm sure many of you know many of these things. Critique uses, misuses, abuses of mathematical argumentation that can be used to intimidate others. Because after all, formal writing, it has a lot to do with algebraic language. And therefore, you need to be over it and not under it. Okay, so now I'm going to talk quite a bit about symbolic transformations and making sense of them. So this is some part of it is going to be my very early work, and some part of it is going to be a little more recent stuff that I've been thinking of. So what I did was to change the classroom discourse to focus on reasoning, thinking, generalizing, and communicating. A lot had to do with communications. Algebraic thinking and activity included, one, to work on symbolic manipulation, and second, to work on pattern generalization, justifying, and so on. What I found were some meaningful concepts like terms, equality, expressions actually supports this understanding of signs and symbols of algebra. Using students' anticipations was very important, which they had formed in the 5 years of their arithmetic instruction. Refocusing this attention on expressions and values, and on the one hand, and then what we call the invariance of values, which is values which don't change and when and why they don't change. And that's the whole, actually, a lot of algebra. Why doesn't something change under varying conditions? Uh, and I connected the structure of the expressions, which means what constitutes an expression and how they relate to the value with the procedures. How do you evaluate or manipulate or simplify expressions? So this is a very, very skeletal understanding of what I did. So I moved children away first from saying that 2 plus 3 is 5. 2 plus 3 is only one possible way of saying 5. But more importantly, 2 plus 3 is also a way to communicate that it's a number which is 3 more than 2 or 2 more than 3 or sum of 2 and 3. So using these words which are relational now, more, less, more than, less than, product of, quotient of. So we moved our attention away from finding simple values to such two-termed expressions to a more complex relational understanding of what things can be said about 5, which includes several things on the left as well as on the right box. 1 plus 4, 10 minus 5, all of this are. And from this, we started generalizing. If x plus 2 was 5, then what will be x? And eventually asking, but what is x plus 2? So just as you said, it is 3 more than 2 or something, 4 more than 2. This is some number added by 2 or 2 more than any number. From this kind of understanding, we move to something more complex. And so the double-sided arrows just indicate we move back and forth between these. And the single-sided arrows basically mean that I did first those and then later these. So here we looked at several of these pairs of numbers where they had to put less than, equal to, or greater than symbols. But they were not allowed to compute. No computations were allowed. They had to only look at these terms. And we had defined terms in certain ways, and I would give you examples of how we define this term in very, very user-friendly. So they had to do all of these kinds of problems, and they had to solve expressions or simplify expressions of these kinds: 23 minus 10 plus 5, or 13 times 16 plus 16 times 12 minus 16 times 7, and they had to do things of this kind. Now I will give you some small snippets of what children actually did. So when they were comparing things like 54 plus 67 and 52 plus 69, they said 54 is 2 more than 52, 69 is 2 more than 67. That's one kind of statement. In the left-hand side, take 2 from 54, add it to 67. It will become 52 plus 69. And or you could do the same on the right-hand side. And this child also said 2 minus 2 is equal to 0. So one thing is increasing by 2, the other thing is decreasing by 2. Similarly, when we gave them 326 plus 598 equal to 924, then we said, we gave them 324 plus 598 is 922. And then they said that 324 is 2 less than 326. Therefore, 924 minus 2. So you see that how their previous experiences and expectations of arithmetic is actually driving some of these. These were not explicitly taught, but they were able to produce some of these. So, when they got some hang of integers, they also started writing integral statements, statements with integers to say that 53 is 1 more than 52, 38 minus 38 is 1 less than minus 37, therefore these must be equal. Similarly, 75 is 1 more than 74, but this one also considered 29 as 3 more than 26 without noticing the negative sign and got it wrong. So they were trying to work without computations and by reasoning alone. This is what we meant by terms. So we basically made the entire expression additively composed. And by additive composition, we gain the possibility of both commutativity, through and through commutativity, and through associativity. And that's what actually helped us a lot. You would see that we also made them into boxes so that at no time they forget what is the unit of composition of the expression. And you see these several examples of what children actually did. They also found easier ways of computing things, as you can see in this C, that 47 and 52, 6 minus 6 and plus 9. So, and they looked around for these. Similarly, in the 12 times 9 plus 16 times 5 minus 17 times 9, you see that children looked for some distributive property here, and they applied distributive property twice. Now, having done these with the arithmetic, it translated quite easily to algebra, because then there was no conflict between arithmetic and algebra. Arithmetic as being driven by finding answers, algebra being driven by using properties. So we had broken this sort of barrier between arithmetic and algebra. Not only did they solve those, they also explained what will be the values. So if the simplified expression of 5 times a plus 6 minus 2 times a plus 9, if the value of this is 27, then the value of the initial expression must also be 27. And the child is asked why, and then the child says, because it is an equal expression. So we have manipulated and simplified the same expression. So very clear understanding of when you manipulate in such a way, or you transform expressions in such a way that the values remain the same. There is no change in the value. And then the child is also asked, can a times 3 plus 15 be written as 18a? And then the child says, no, this is a product term. You can't move your 15 to the times 3. And therefore, this can't be done. Similarly, children also engaged in writing expressions equal to these. We gave them some expressions and told them generate as many expressions which are equal. Now, this was akin to asking them make questions for which this will be the answer. And they made attempts. Sometimes they were wrong, sometimes they were correct. But what we found very surprising was students actually explained to us that given these two very big expressions, 24 minus 13 plus 18 times 6 and 24 plus 18 minus 13 times 6, this child says actually 24 minus 13 plus 18 times 6 is a bigger expression. And why is it bigger? Because 18 times 6 is there, which would give a more answer. And here minus 13 times 6 will give a less answer. So we found that children actually consistently learned to use the idea of terms across whether they were doing procedures or they were thinking about some anticipated value of expressions. Now we come to something more. So which is that we also not only did that, we also tried, once we had children had reasonable mastery over those ideas, we move them to something else, which is generalizations and some conjectures and so on. So this is a matchstick pattern, and we ask them several questions. So now what was interesting about this is that children, because they had so much facility with the expressions, they started by writing expressions of different kinds. And this is just 4, and I will show you some more, which can be very closely linked to what is the picture. Sorry, I'll just remove this for the time. So the first figure, the child says 4, then the second one has been done by adding 3 more. The third one requires 3 more than the previous one. Now, this is a very recursive relationship. And oftentimes, children actually find it very difficult to move from that. For every new figure, you need 3 more than the previous one. Now, if you only have this understanding, it's very difficult to move to a functional relationship, which is what we want as a rule. 4 plus m minus 1 times 3. Now, this is where they used all this understanding, and it's quite amazing for us that they used all their understanding of expressions to actually write all of this. That they wrote these plus 3 when they actually felt that it was becoming too much of plus 3. Then they also converted the plus 3s into some 4 times, 5 times, whatever was required. Similarly, they saw it as different ways of counting. Now, so there are 2 approaches to doing this. One is to say, this is the input number, this is the output number, figure out a relationship which matches the input to the output. That also is not bad completely, but then there is no meaning making, and representations in those, the final rule, algebraic rule that we want for the input-output relationship, is very hard to arrive at. Now, pictorial representations in that sense support children to count in different ways. And not only that, it also allows them to make representations which are in sync with how they were counting. And that's what I wanted to bring to your notice. So we at least found in this very first lesson of pattern generalization, 7 different things, 4 of which they could actually tell us how they were counting. There were 3 others which were in very different realm of reality. And these children were just toying with different expressions to fit one which matched the output, which are these 3 that I've now just projected. These can't be easily understood from the picture itself. But they did many manipulations, iterations here and there, and they said that these will also equally well work. We also played games, and we asked them this is this famous game which is called the Think of a Number game. So you think of a number and I tell you to do several steps, and in the end, I will be able to tell you what answers each of you have got. Initially, of course, they did not figure it out, but over a period of time, they actually figured out what we were doing. At some point, we gave a slightly simpler such set of steps, and one child just got up and said, "Oh, so you are doing this. You are asking us to add something and then take away something. And sometimes you're asking us to multiply something and take away so many times. And therefore, it's the same." And then it was sort of paved the way that now that you figured it out, can you make your own? And children made out. They worked with numbers first. Then they worked with the expressions to sort of prove that their answer is indeed correct. We did some more of this in calendars, and children saw simple things like neighboring numbers, diagonal number, left diagonal, right diagonal, tried to make representations. In calendars also, they tried to do several things and tried to find if there were some commonalities. Now, these were some motivations for learners to explore and hone their skills of working with symbols. So this was just an extension for them. These were opportunities which are significant for algebraic thinking: noticing, describing, representing appropriately, identifying patterns, generalizing, and providing some arguments. Even if they were not foolproof and sometimes incorrect, because of their limitations of representational capacities, we found that these were significant opportunities for algebraic thinking. Now, in the more recent, what we have done is we have put some of the numerical work in tasks of this kind, and I pull out from the new grade 3 and the grade 4 textbooks. These are preparations for doing this in perhaps grade 6. So looking at several patterns, how 100, 200, 300, what will happen? If you have numbers like 7, 8, 9, 3, 4, 5, 1, 2, 3, then what happens? So if you have numbers with zeros, how many such numbers can there be? How many such numbers can there be with 1, 0? How many can be with 2? If you are multiplying, can you see this multiplication thing? Can you find some more examples? We are not even asking them to think why it is happening. Just preparing them to even notice things like that. These things can happen. And can you find some other examples for something similar? Hopefully children will do. So things like take a 2-digit number, take its reverse, add them. What numbers can you get? Can you get only 2-digit numbers? Can you get 3-digit numbers? So leaving it just at the level of numbers, which perhaps when they start doing algebra in grade 6, 7, they should be able to revisit them and now use more generalized arguments, probably using symbols. So some quick summary. Symbols need to be explicitly discussed and endowed with meaning. That's, of course, this is true for across mathematics, not just algebra. It's the same with large numbers, it's the same with fractions, and it's the same with rational numbers, integers, whatever. Meaning of ideas is actually successively elaborated by students in the process of acting on them and reasoning in them. So it's not the case that we develop meaning and then we work. This is a cyclical process and we keep going through it. So in the case of algebra, we found there were some conceptual tools necessary for doing this and uniform rules, which we found in the idea of terms, equality, and expressions. Uh, Thinking of expressions both structurally and procedurally were also very, very crucial. It was a very useful insight. Now, algebra as a tool for expressing generality and convictions is actually a very powerful motivation. And this is something that we can do all through schooling. Explorations with numbers, arithmetic expressions, identifying patterns, providing examples and counter examples. This is what probably we need to do now all through. I mean, these are some other questions. This is I'm sure many of you will know this. Find the sum of two numbers when the plus, you are supposed to use a calculator, but the plus key is dysfunctional. What can you do to do that? It's actually a very, very nice task. Looks a little silly and dumb, but with different kinds of students, I have found some very enriching things. And you can do several kinds of visualization now. So this is a very simple visual for sum of consecutive numbers and why they're always squares. So you can see 1 plus 3 plus 5 and so on. Thank you. I hope I made some sense and I stuck to the time.
Thank you, Rakhi. I think, Varsa, why didn't you? Yeah, you'll take some questions and comments, isn't it? So we're open for interaction, but Varsa, please.
Varsha, did it make sense?
It was quite enriching and elaborating how we can make sense of algebraic symbols and signs. If anyone has any questions or want to have some clarification on any of the slides, if they haven't understood, they can raise their hands and ask. And maybe unmute yourself. Praveena, please unmute yourself, and ask.
Yeah. Hi, ma'am. Thank you very much. It gave the flow of how to teach algebra and what are the mistakes they are making. It's a very nice presentation. For me, I have do you have any recommendations or any documents which talk about the steps, how it has to go, that flow? Is what I thought of asking.
Okay. There are recommendations, but see, I have taken a very small slice. This is only one way of doing algebra. You
Okay.
could do algebra in several other ways. It is the starting point which decides how we progress. If you start with the assumption that I need to make sense of the symbols first and some transformations on symbols, this is the way. But I could actually start from the end by saying generalize. And nowadays, I also try doing this with children. Do generalizations with several kinds of patterns, not just growing patterns, but also repeating patterns. Let children talk out the generalities and the commonalities that they see across different instances and slowly convert their talk into symbols. Anything is laborious, there is no easy way. But that could be another way. Places or countries or cultures where there is a lot of handheld calculators or technology support, they also start directly from graphing. They don't have to plot the graph, but the computer generates the graph, and you can understand what different terms of the function actually mean. So there are several ways. We choose the one which is comfortable and convenient for us. Now the trend in 2010 onwards perhaps has been even grade 1 2 children are engaged with generalizations, not symbolization, but generalizations. Take patterns, generalize, talk about it, but don't um, uh, don't use algebraic symbols. That's it.
Okay. Okay. Thank you.
No, I got distracted with G-nuts problem solving. Sorry. No problems, G-nuts. There are many, G-nuts. There are many linear ways also, not just quadratic.
Anyone else? You can unmute yourself and ask your question. Or maybe any comments or clarification.
It either made sense or it didn't make sense.
Rachna has posted that she's asking algebra in our culture, how we can understand, or make sense, articulate algebra in our culture, like folk
I
mathematics.
mean, you do have a lot of these columns and rangolis, which are examples of that. I'm not sure whether they're simple or complex, but you could do some things around it. And I'm quite sure if we dig a little bit more, we will also find puzzles, which will include some of that. There are also a lot of it in art. So growing patterns. So I mean, basically all of these fractals at the middle school level, fractals are primarily generalization tasks, and there is a lot of it there.
Aniga is asking, the doubt I have is that in which language do the classes sessions took?
Okay, so I mean, for very practical reasons, the children came. We taught several kinds of children. I taught a section which spoke, which had migrated from other places, but they studied in an English school. My friends and my colleagues taught in Marathi to children who spoke only Marathi. Because these children came from an English medium school, they of course spoke English in school, and they were fined whatever 1 rupee, 2 rupee if they uttered non-English words or sentences in school. However, in these classes, we were very happy to have it in any language actually. Primarily, they spoke Hindi or English. English, or a combination of it. But actually, I should also tell you that the Marathi kids that we had, their level of articulation and communication was actually outstanding. Once they got hold of it, it had no match with this combination of English, Hindi, Tamil, Malayalam. It couldn't, yeah, it was very, very sophisticated. The way they wrote their reasons, with the way they thought and articulated, it was, yeah, it was quite amazing. I'm sure. See, any knitting, carpet weaving, all of these require a codification of patterns and therefore has some algebra in it. Correct. They are as much algebra as much as patterns, geometric patterns. See, when you say algebra, no, oftentimes in our heads, it also means that I will be able to arrive at a general rule. Now, whether all knitting, carpet weaving, or sari border or sari, let's take any of these Andhra or Odisha, any handloom. Am I going to be able to write a general rule for it, or rule for different rows, different rules for different rows? That's a concern. Maybe that should also be possible, but that's hugely complex. It's more, in that sense, a more geometric analysis of it is more elegant rather than an algebraic analysis of it.
Hi.
Hi, Jayashree.
Good, yeah, nice. See, I very, I think, this whole, there's a different, I think there's a difference between being able to, uh, think in terms of, okay, like I mean, as we were all involved in making columns when we were very young.
Yeah.
So, the arithmetic progression that one has,
Yeah.
one knew how to do that. And I think that a lot of people will know. But that does not actually, I'm wondering whether that actually connects up with being able to think symbolically also. This generalizations that we are able to do from a certain kind of a geometrical context or some kind of a numerical context in which one is doing it, and then to be able to, I'm just trying to see whether there are actually contextually this kind of thinking is slightly different. I mean, can that jump that you are saying is that link has to be made, that that you have to, so you can, I'm a little bit wondering whether actually I can say that algebraic thinking has been there, because I think algebraic thinking includes also the ability to be able to think in terms of manipulating symbols.
Yeah, surely.
Here,
and use symbols comfortably.
Very primitive. I think there is a certain amount of generalizability alone that's there, and that generalizability itself is not even thought in symbolic terms, but in certain kind of a
Inactive
mental image. Yeah.
It's an inactive thing rather than a symbolic.
Right.
It may not immediately connect unless you make people see some of this. It's possible that when you engage with things like that, you might also be able to see what I do there in that world of my life early in the morning. Or I might just suddenly make sense of it all in one go. Yeah.
in a way, I mean, another thing that we need to also keep in mind is like, this always happens, that we read what we want into what exists already.
Yeah. That is true. That is true. That is true. That is true.
And in that sense, actually, there was a question about culture. So culture itself, therefore, it is not. I mean, it's very difficult to answer if it is there in our culture or not. What is it that we are thinking? Are we thinking in terms of representing symbolically? Are we thinking in terms of? That's a question that one needs to ask. Being able to, some kind of a generalization that's not coded in some symbolic terms.
I mean, there is a symbolic world also which has existed since several centuries, but then that's very complex.
That also is not available for everyday
That's not
life.
available for everyone. That's not available for everyone. Yeah, that's true.
Yeah. Anyway, let me not grab all that and use that time.
Sure.
Okay, Rachna again posted a question. One last question, ma'am. So, when I see my child doing small work in mathematics, like expressing quantities, I'm able to understand what he's saying, but explaining to him in his language becomes difficult. Do small children have different views of quantities or seeing mathematics? And if yes, how to have dialogues with them?
And I think we don't need dialogues with them, perhaps. Let's not push them into dialogic world. Let them do. You see, I think when we work with very young children, one of the things, this is also all my hunch. I'm not necessarily worked with very young children, but and that's true for older children also, what I'm going to say now. So we try and understand what the child is doing. From what we make sense of what the child is doing, we give them some more experience and we try and affirm or contradict our own first hunch. So with children, we probably can't get into a negotiation of these symbolic meanings. But what we can do is to keep producing more and more experiences for the child, which helps me form a sense of what the child is thinking. What the child is feeling about quantities, or how the child is interacting with quantities rather than shapes, versus quantities versus objects. Does the child even quantify, or is the child playing with objects? So there are minute things which probably you will have to notice, Rachna. No problems, Rachna. It's been several years.
Biren, you can unmute yourself. Yeah.
Yes, and you can show yourself, Biren. Hi, Biren.
Hello, ma'am. How are you?
I'm good.
It's
How
been
are
a long
you?
time.
Yeah.
Good, ma'am. Doing good. Yeah, it was very nice to hear from you after a long time. Last time it was in the classroom.
More or less the same, isn't
Yeah.
it?
I'm actually excited to, I saw the notice and then I thought I should join somehow.
Okay. That's nice.
So yeah, thank you so much, ma'am. It was a wonderful session. And actually, just wanted to share that I am working with a student now, and he just passed out from standard 10. So he was a COVID batch. Means it was during the COVID time. He was introduced with the concept of algebra, and he was in standard 6 or 5 maybe. And what struggle I faced while teaching him was that he did not know the concept of x or unknown variable and how to find it. So somehow we had only 4 months to work with him. So somehow I did not teach him algebra at all. I said rest of the subjects, rest of the chapters, you go ahead, and then he just scored pass mark 30, 35, and then now I have to work with him with the algebra and other chapters so that he would give a improvement exam. So this session actually helped me to think those critical questions, like how can I introduce to him? Like I have to go backwards now. He's in standard 10, but I'll have to teach him standard 5 and 6 concepts, and then help him with the concepts. So this session actually helped to frame those questions, generalizations to introduce to him. So yeah, thank you so much, ma'am.
So in fact, Biren, for you, most of the things actually you can help him through. If the child is comfortable with some arithmetic, that you could use to help get into algebra. You could also do these puzzles. This was a lecture, so I didn't want to make it like a puzzle solving session. But there are nice ones, including the grade 3, grade 4 book examples I showed you. For slightly, why does it happen? Does the child...
Sure, ma'am.
Yeah, why does this happen? Yeah, that's probably important.
Yeah, thank you, ma'am.
Yeah.
Okay. Hi, Rakhi.
Hi.
Can I ask a question?
Hi, Anushri.
Hi, I don't know if you remember me.
Of
It took me
course.
back to the classes.
Of
Yeah.
course.
Yeah, so I was wondering, so JAM actually talks about the Indian school education system where calculus is at the top of the tower, and so you talked about how arithmetic to algebra children use that kind of a thinking, and they bring that to algebra when they start learning about it. So I was wondering, is there a similar sort of transition that happens from algebra to calculus as well, and is there a
Sorry,
way
once
for
again,
us to
Anushri.
facilitate?
I missed your... What is the other transition you spoke about?
So you had given examples of how arithmetic thinking, what we do in arithmetic, translates into
Now I got it. Yeah.
algebra.
So algebra to calculus.
Yeah, I was
A
wondering
huge
if
jump
there are
of faith.
Yeah.
Huge. So we believe, see how does our mind generally work in regard to education? No, we believe, what is there in calculus? You only have to calculate limits. Limit calculation is limited to calculations. You plug in those values and find it, and sometimes, okay, for x equal to 2, maybe it will not work because there is x minus 2. I mean, it's computational, right? So we believe that these understanding, I'm not saying, therefore, polynomials is not important to precede it. Because after all, you do much of the calculus with polynomials. But the ideas of everything in calculus is so very different. There, the object of analysis is not expressions at all, or polynomials not at all, except for in terms of derivability and whatever, whether something is continuous or has a limit. Yeah, so the object of analysis is very different, and therefore I think it's a much, much worse transition than this one.
Gina also. Anyone
Yeah,
else?
what is the question, please? Gina, can you just ask that?
Yes, can you hear me?
Yes.
This very celebrated foreign paper where they argued that they introduced algebra to 1 or 2 grade students using pattern generalization. And then, okay, that was my very impressionable time. So I got impressed. I thought, okay, this is the approach for introducing algebra. Because with algebra, we find it very difficult to bring in very realistic examples or something. And the only examples we had is word problem. Word problem is the way to connect algebra to real life. But when we are looking at the arithmetic approach, which is actually having a conceptual, though it has a rich procedural knowledge. So, like, how do we now see that? Like how do we see these? We integrate this approach, and how do we see integrating this approach? Or because it also is a challenge, have the arithmetic approach and make students interested. Because if the question is to connect it with real life and make it realistic.
Yeah, I mean, if you have to use arithmetic, you have to move away from reality and ask a meta level question now that forever in your life you have solved. Now tell us how two problems are similar or different. So you have to still intrigue them with something if you do arithmetic. And of course, many of these problems, so let's say the mind reader, it's a very good platform. Why does something happen? Correct. So when you look at those numbers again and again, you keep seeing that there is something happening every time. When you can make several mind readers, that's only one. Why is it that whenever you have a 2-digit number and you reverse the digits and add them, why is it always a multiple of 11? Why does it happen? Now, if this can excite children, I think there is some promise in it. And then doing things of these somewhat realistically thinking that suppose the plus sign is missing, suppose the minus sign is missing. I mean, these are ways of putting the problems. I have also seen tasks where you have Excel sheets and you say that I have two variables A and B. Okay, I have added these two and they have given me a 9. Correct? Can you write other expressions in the Excel sheet? So I create a formula basically, which should always give me a 9. So what am I doing in the process? Of course, there is an interest on the 9, but I'm also writing equivalent expressions. So what format you choose, I think it is the matter. And what format we choose, we try and choose in such a way that we are able to communicate to our children and excite with something. Now, the problem is that when as teachers in classrooms, we start by saying, now we are going to start a very hard thing. Actually, you know, there is nothing real in this life about this. There is no reality of algebra. But we still have to do it because higher education requires it. I think we explicitly need not make this thing that now you will do algebra, tomorrow you will do calculus, and then you will become an engineer. I think that's the problem. We have to become terribly conscious about what we tell and what we don't tell. We necessarily should not communicate to children that all mathematics is for doing shopping in this world. So, but Jeanat, on the other hand, there haven't been too many of these arithmetic algebra things. Huh? There was a little bit of that which happened in Israel. There was a little bit of that which happened in South Africa. And there was a little bit of that which I did. But nobody has picked it forward. That is one. Of course, there are challenges because all the time you can't keep going to arithmetic, one. But on the other hand, you could always teach things in such a way that algebra can just use them. So that's another thing that you can do. The other is that doing nice problems. So something like, say, what John Mason would and Anne Watson would do. Right? Levels and levels of variations in problems and generalizations. I think those are nice for any context, even if you don't have resources. But that's wonderful. In fact, so doing something which uses numbers, whether it is the flash mind reader, whether it is doing these kinds of problems of invariances, that you do something and the answer always remains the same. All these problems, the good part of it is it works on numbers first. And numbers, by the time children come to algebra, are concrete for children. I'm not very sure whether children actually are looking for real world solutions. But when we make it that it does, other than simplification and solve equations, there is no purpose of doing algebra. Then there is a problem that say that, so I hear often in PTMs, children and parents saying, and I overhear this, till my life was perfectly fine till I had I had to deal with English alphabets in math books. And that's because they're doing very constrained problems. They're not doing something which is either a puzzle or a riddle or a problem solving. And I think that's the problem. So there is a lot of functions today, but this is on the other side. If you have calculators, then you can probably do that.
Whole thing of, for all of us, I think at some level, when we are making statements, when we want to know whether they are true or not, the one way to do it is to put them in symbols and then, work it out. Isn't that right? I mean, I mean, that need not eventually end up in, engineering, mathematics, or calculus or something like that. I mean, this notion of prove something, simple thing, proving something.
Yeah.
Simply like sum of two odd numbers is an even number.
Even number, yeah.
Simple, right? Right. I mean, at the upper primary, you could actually make them do that.
That's another thing, actually, probably, which I didn't focus on too much in my, I mean, I didn't say this explicitly. We have done both things. Writing a statement saying, tell us why this is true. And more recently, I've done the opposite. This is the step of things you should do. Tell me what is common to all of this. In fact, that we did even towards the end of my work. The second one seems like a little more amenable to children. They get really perturbed when it is my agenda that they have to or why it might be so. These are very small things because the word proof seems like terribly difficult for children. And also, we also have very high standards for what it means to prove. And you should write like this, and teachers drill them, but they don't get it. And they don't own the statement.
Anyway, I have not experimented. You have done so much experimentation in the classroom.
I just do with the also students. Yeah,
speaking from some kind of a reflection. And
yeah.
There's something from Rachna again.
Yes, Rachna.
She has posted a question. What if we don't do algebra? How does it help our brain or in general humanity?
I mean, Rachna, to tell you honestly, several people will be very happy if they don't have to do algebra. But like every other thing, whenever we gave them a choice to have a humanities and social sciences and what is that called? Home science. Girls' schools in rural areas will grab that opportunity. Now, that's very unequitable. And I think at some point I had quickly looked at Arindam's thing about Bob Moses. That's precisely what he would say. That across Africa, US, all the African Americans never sat through an algebra 1, 2, or whatever class in grade 7. They were out of all of that, which also meant they will be only the working class. So it's terribly unequitable not to do algebra in this world. How you do algebra is a choice you have.
Is there any other question from anyone or any doubt, comment?
Just one
Yeah.
question actually. So in algebra, once one starts pursuing algebra, what typically happens is a lot of arithmetic intuition also has to go out, in the sense that juxtaposition is not a place value thing; it's now a multiplication. Similarly, one is also imbibed with a lot of rules that come for free in algebra, such as commutativity, right?
Correct.
When one finally transitions to things like operators or even matrices, right? These things sort of magically go away. I'm not saying magically in the math sense, but how to treat them is not very well explained. This further becomes difficult when one lands up. So, for example, when you do derivatives, right? So derivatives for single variable functions, it's sort of taken for granted that, yeah, well, objects commute, you don't have to worry about things, everything is nice. But the moment you reach sort of derivative with respect to vectors, a lot of this just becomes hard, right? So any sort of way to, so this is sort of unlearning in a sense, right? You have to unlearn the commutativity that you thought was so free, and now life is just different. Right?
No. I didn't get that commutativity point again.
So commutativity goes away in matrices. Right?
Correct.
Yeah. So similarly, when you do gradients with respect to vectors, commutativity is again lost. So chain rule is not the same chain rule that we learned in Calc 1. It changes, right? So how does one sort of help people get used to this? This is problem at a university level. So I
I know that.
the MSc who struggled to do this. So yeah, if you could shed some light on this.
So I was just thinking actually that why can we give experiences? I mean, I don't any longer teach higher secondary or even undergrad students mathematics, but can we give children these possibilities or opportunities to explore in what conditions commutativity works? Commutativity does not work with division also and with subtraction also. There are earlier also situations when commutativity did not work. But there is a chapter in number systems whenever it comes and we trust it on page 1 that these are the properties which guide something. I mean, why did I make it? Children by that time know whole numbers, natural numbers, fractions, rational numbers, integers. Why can't they explore it? Whether it is the same. I'm not saying they're going to prove it because it is not something we prove, but at least they can understand now much better than probably in grade 2 and 3 when commutativity works and when it does not work.
Fair. Thanks. Thank you so much.
Yeah.
Akansha has posted a question. Ma'am, can you please suggest resources which we can look so to overcome the loop of doing algebra in a mechanical way, which our NCRTs accept some examples, make us and kids do.
Okay, so okay, let me just try and put it for you. If I think I kept my references somewhere. One of the books which you can, and where are you, Akanksha?
You can unmute yourself, Akansha, and ask question.
Ma'am, I'm working in a girls' school, Pilani.
Okay.
It's Birla Balika Vidyapeeth Pilani. Yes.
If you can get this book, it will give you loads of ideas about how to do algebra better. So, I mean, I'm really very fond of John Mason and Anne Watson's and Susie Wilder's work. So there are a set of questions. These books are not for how to, you might be doing very similar things in class, but you could change the way you present those tasks for them to become meaningful. So instead of just asking children to simplify as I did, you could also say, why do we simplify like this? What rules are governing this? Of course, we had set those conditions in arithmetic, and children seamlessly seem to have been transferring those ideas.
Yeah, yes, ma'am.
Yeah. It's a matter of some tweak in the way you present your tasks. You could take a look at this book.
Okay, ma'am.
I have put it in the chat.
Available online?
Must be. It's
okay.
I think this is a Sage set. It is called Paul Chapman, but I think they have a Sage collaboration or something. I think you will get it.
Okay. Thank you, ma'am.
In fact, this series has one on statistics, one on geometry, and one more on something which I don't remember. So you could look for those also if you are in a school. Though this is necessarily not for to give away to children to work on. It's for the teacher more.
Yeah. Okay, ma'am.
Yeah.
Thank you. Ma'am, can we also get the recording of this session?
Yes, I will upload this on YouTube channel of NMRC, and then there you can check it out, NMRC JNU. And soon I will post it on the Google group also, links of all the recordings. I will share with you all. And those who wish to, join the upcoming sessions of this seminar series, they can also drop their email IDs so that I will add them to the Google group so that you will get next notification for the coming seminars. Yeah. Okay. Any other question?
30.
Ma'am, I was thinking, because I was for a brief period of time, I was I was part of Azim Premji Foundation. So when you were talking about, how children, articulate the symbols as objects. So I have seen this tendency in teachers also. So
Yeah.
how we can actually address this problem of problem in algebraic thinking in TPD of mathematics teachers and teacher educators, you know?
So we have to, so like the transcript I showed, it is a classroom transcript. I haven't cooked it up. And nothing today I have cooked up. I generally cook up loads of stuff, but today I did not. But it is real, right? Teachers are using it as short forms. But then you have to sort of keep asking more and more questions. So one of my questions is, haven't we in primary grades always added 8 pencils and 5 rubbers? Haven't we always added in primary school 5 apples and 2 bananas? So we didn't use a variable then. Why are we now thinking that 5 apples and 2 bananas must be written as 5a plus 2b? Then you keep pushing them. What does it really mean? What properties are you applying? Then they will say we are adding like terms. There is a common factor. If it is a common factor, then is pencil a common factor? I mean, you will have to keep doing this. You have to set out some way of leading them to the conflict and then resolving the conflict. If you leave them with it, they will be very dissatisfied.
And also there is another problem is that there are not many workshops for middle school teachers, and generally in mathematics workshop, I mean, pre-service or in-service teacher training workshops, there are many lectures or sessions on algebra. Actually, mostly it is focused on operations and primary mathematics, arithmetic mostly.
That's also true. Yeah. Not too many of us have worked on too many middle school ideas.
Yeah. That's true.
Then Rakhi has to come back again to give a talk. Maybe take up some more questions on algebra or the dialogue to another level and give another talk. Yeah, we are compiling all these videos so that there'll be one, source where everybody can draw.
Access them.
Rakhi, can I just ask you one small question? It's not a question, actually. I'm a psychologist, and by training. So, have you read Davidoff? Then I'll ask. Otherwise,
I know a little bit of Davidoff's work, but I haven't read very deeply or anything.
Okay. Is he said, I mean, he picks up several examples from children, and he says, okay, if I give a handful of, say, toffees, I'm just giving you offhand an example. I didn't give this example, but examples like this, a handful of toffees to one child, say, a 2 or 3 year old child, or 5-year-old child, and then I give just 2, 3, significantly a lower quantity to another child. And then I ask very young child who doesn't have access to numbers, or at least hasn't started using numbers. I ask that child, okay, who will be happier? or I pose a question of this kind, is there any problem? Or which child will be happy or which child will be sad, and the child, if it is a desirable object, the child will say obviously the one who gets more, significantly more. So this child will be happy. So the next question is posed like this. So what do we do, And the child may, say that, or may take away some from the child who has more and give to the child who has less, or we'll say that give some more to the other child, not taking away from this child, but give some more to other child. The child, provides different kinds of solution, and he brings examples of this kind, analyzes them, and says that, look, we are not wired for arithmetic. What we are wired for is algebra. Okay. The child is fundamentally doing algebra and knows that there is more in one place, in one pot of with one child. So we take away, but the child is concerned about equating. I mean, he's constantly equating the quantities, and he's not asked to equate, but he's equating the quantities, and he's trying to make the quantities equal. And when the child has numbers, then child can give you a very exact kind of equation. So you say that this is the child does even before the child gets numbers. So uses number as an artifact to count or compare the quantities. So what we are wired for is algebra, and arithmetic is cultural, it comes from outside. And then it has a huge implication for teaching of algebra and arithmetic. It reverses the order. Starts with algebra, moves to arithmetic, but their symbolization become one of the major thing to start with. So, I mean, there are many more things he does. Of course, experiments with children, exposing them to 3-year program where he moves from algebra to arithmetic, and then gives tasks to these children, and then to undergrad children in UC Irvine, and similarly some other universities, and shows that these children outperform. And then the children have better conceptual understanding. What is mathematics falls in place? The reflexivity is little more. So suppose we use the insight that these cognitive experiments give us. How do you what kind of things you do in teaching of algebra, which might create a very different kind of reflexive capacity or access to the way arithmetic works? Children. You don't have to answer.
I mean, I know of something else also. Or a slight adaptation of this, where they started with not doing whole numbers, but introducing numbers through measurement. So these children understand numbers only as measures. Measures, ratios. So multiplicatively, everything is understood in this world. But I don't think they got the same facility with algebra immediately. I mean, they had to struggle some bit, is what I remember. It's been several years.
No, it wasn't very popular in the sense.
It was only limited to that, but they did some very interesting work. They did some very interesting work.
The reason I'm asking is that, many times children, pass with very high marks in mathematics, but mathematics doesn't fall in place for them. And but some experiments of this kind suddenly changes the way we look at mathematics.
No, I was actually, in response to your question, I was thinking, so Euclid had some of these axioms: equals added to equals is equal. Equals added to unequal quantities doesn't change the inequality. So these, I mean, what you said earlier about Davidov's work is very similar to this. If I have 2 + 5 and I have 3 + 4, then I can add 2 to both and keep it, and children
Mm.
might feel that these are the same.
Yeah.
Very young children might have this sense.
I know.
Yeah.
Equals added to equals is an axiom, right?
Yeah. But these
What did Jaspreet say?
experiences you may have is what I'm saying. Yes.
Jaspreet broke. What did you say?
I said it's axiomatic.
It's axiomatic.
Right. Yeah.
Yeah, in 6th and 7th, we were actually trying a little bit of doing some of this, just to give them this feel. But it was very hard to write something around this. We had started, but we didn't quite achieve what we wanted. To do
Rakhi,
these.
with foundation, do you get to have any kind of a thing with the foundation people? Do they have a reach to a large number of...
Correct.
Do they... Middle school level mathematics, we have somehow not gotten there. Huh?
Yeah.
Massive experiments at the middle school level, we are still stuck at the primary.
Yeah, that's right. Yeah. We tried in southern, the tribal areas in southern Odisha. And but we had slightly different kind of objectives as well. One of the objective was to introduce the arbitrariness of the symbolic symbols that we use in algebra, in mathematics,
Absolutely.
And so how these are just agreed upon symbols which can be replaced by other set of symbols if the community agrees to use it. So that arbitrariness, to get that understanding about arbitrariness, we use some of the Davidov's examples. Not necessarily. We didn't use it because the schools were anyway moving from arithmetic to algebra. So we didn't want to disturb that in any major way. But we used for 2 reasons, I remember. This was done more than almost 18, 19 years back. And when I was doing my ethnographic work in Saura area, we did that with 2 purposes. One, yes, talking about, this, making students realize that the symbols are only the product of practices, and therefore arbitrary. The second, we thought, we were concerned about history of knowledge, When students engage with any kind of knowledge, they also develop a historical understanding of how this knowledge might have developed or what is the nature of this kind of knowledge. So for that, we thought some of this, like counterintuitive ideas that, look, we are not wired for arithmetic. We are wired for algebra. But if we are starting with arithmetic and moving to algebra, so if we are wired for algebra, what we do with maximum facility that the brain gives us. But yeah, this was to develop a kind of a meta-mathematical in reflection. And so because we were working within a broader critical paradigm of multilingual education. That was multilingual, multicultural education we were experimenting with. So this was, I remember, one of the objectives, that how to create some of these reflections in students, They don't develop the theory of it very quickly, but it creates their capability to learn.
Yeah. So in fact, this is another thing that I quite like. Dave Hewitt. It's called the arbitrary and the necessary. So it's basically a reflection on curriculum.
Yeah.
But it's a lovely paper which helps us make this delineation of what are good, which questions are why questions, and for what things we can't ask this why question, we just take it.
Okay, yes. Versa takes 2, 3 more, then we can. But this has been a very interesting session.
Thank you so much.
I was loving it.
Thank you.
Does anyone have any question? Anyone else? Any question, comments, queries? Okay, I will take it as there are no questions. So I will go ahead with binding of the session. So thank you so much, Rakhi ma'am, and joining us.
Thank you, Varsha. Yeah.
Yeah, I mean, it really made many of us think that there are so many ways of doing algebra, and maybe we should go ahead and explore that. And maybe I think there should be a moment of reflection of how we have learned and understand algebra and in a school and for later in life. Maybe school generally it's difficult for everyone, but later how we have understood and articulated that, and also how we have developed algebraic thinking. And yeah, so thank you so much for joining us. Thank you very much, ma'am. Those who have joined today for the first time, please drop your email IDs if you want to join next lectures, and I will add you into the Google group, and so that you can get the notification for the next lecture. Okay. Thank you.
Thank you. Thank you, Professor Panda.
Rakhi, you'll have to come back.
Yeah.
I'm getting Arindam back again.
Okay.
Maybe in May.
Okay.
So, because otherwise, let the audience can stay with one, scholar for at least 2-3 lectures, and that's when they get the scholar full.
Yeah.
So
We will
I'm
discuss
planning
what
to
you
bring-
would want me to talk about. But
Yeah, we will discuss over phone.
yeah. Yeah.
But
Sure.
just one lecture. This was a wonderful.
Yeah,
But I
thank
want you to also develop it to another level and
Sure.
bring some more questions and some more of your work to reflect on algebra. So maybe we are just giving a gap of 2-3 months.
Yes.
And maybe 2 months, and then
Yeah.
hear you back. That's okay with you, no?
Yes, yes, yes.
Great. Thanks, Rakhi.
Thank you so
Let's
much.
also meet
Thank you.
in future.
Yes. My coming to Delhi has significantly
Yeah, please,
reduced.
yeah. Let me know.
But if you're coming, then please, we can
Yeah,
meet up
I'll
in
let you
Bangalore.
know. Right.
Yes, yes, yes.
Thank
Hi,
you.
Ram. Thanks so much for
Yeah.
coming again.
Okay, so we can leave now, Rakhi. Thank
Yes,
you.
yes. Thank you so
Varsha?
much. Bye.
Yeah,
Bye-bye.
bye.
I'll stay here for some time. Yeah.
Yes.
And thanks everybody.
Thanks,
Bye,
everybody.
everyone.
Thank you. Bye.